So hello everyone and welcome to this next video lecture on my circuit simulator Python Power Electronics, and this time the topic will be how to simulate a photovoltaic panel. So to begin with, I'll just talk about some basic terminology which is always there with the PV panel, and these are the test conditions which are always specified in the data sheets. You'll find usually two major test conditions specified. So the first one are the standard test conditions. The standard test conditions are basically ideal conditions, and that is defined as G is basically the incident solar radiation. So G is designated as Gref at standard test condition and is equal to 1000 watt per meter squared. The temperature of the cell, it's important to note here, this is the temperature of the cell, and at STC it is designated as Tref, and that is equal to 25 degrees Celsius. And it's very important to note here, this is the cell temperature and not the ambient temperature, not the atmospheric temperature. The other major datasheet value is the nominal operating cell temperature, NOCT. This could also be the nominal module operating temperature. It goes by various names. You'll have to check out what it's called in the datasheet. But this is basically the nominal operating condition. Unlike these standard test condition, which is an ideal test condition, this is the test condition which is usually what is found when it's operating. And at these conditions, the temperature of the cell is 45 degrees Celsius as opposed to the 25 degrees Celsius in STC. The incident solar radiation is 800 watt per meter squared. It's not considered to be 1000 because ideally quite often what you see is 800. And this usually occurs at an ambient temperature of 20 degrees Celsius. Alright. STC does not mention anything about ambient temperature. All it says is the cell temperature. Nominal operating cell temperature usually talks about ambient temperature. Okay, so now that we've talked about the basic terminology, I'll show you some of the parameters that are usually found in a data sheet. And these are sample data sheet parameters. I'll just go through them quickly. So the three most important, there are lots of parameters, but the three most important ones that you must look at are these three. First are the electrical data at standard temperature conditions, which I've already talked, standard test conditions, which I've already talked about. The next are the data at nominal module operating temperature. Like I said, it could be nominal operating cell temperature or it could be nominal module operating temperature. In this case, it's an MOT. And the last are the temperature characteristics. So I'll just go through them. At STC, depending on the different power rating of the panels. For example, this particular one, which is a Canadian solar panel, has several ratings of PV panels. So they're like ranging from 275 watts all the way up to 290 watts. And in each case, you will see at the standard test conditions, they have mentioned the maximum power, the voltage at the maximum power point, the current at the maximum power point, the open circuit voltage, right, the short circuit current, and some of the other stuff, the module temperature. Now, some of the other stuff we will not really use. These five are the most important. That is maximum power point, voltage at maximum power point, current at maximum power point, and also even more important than that are the open circuit voltage and the short circuit current. We will need these last two, that is open circuit voltage and short circuit current, for determining the parameters of the circuit. Next are electrical data. The electrical data, this is what happens at nominal module operating temperature. Now what's important to know here is if you compare these two, that is if you compare the first column for 275 watts and you compare the first column here for 275 watts, you will see that these values are much lower. And that is because this is at a cell temperature of 45 degrees, whereas this is at a cell temperature of 25 degrees. That's what shows. The result is there are more losses in the module at 45 degrees than there are at 25 degrees. The last are the temperature characteristics. Now, to know about the temperature characteristics, you need to look at the characteristics here. You can actually plot the voltage of the panel versus the current of the panel as a characteristic in this form. Now, when you do so, you will get this curve. And this curve changes with solar incident radiation and temperature. So first on the left, they have changed solar incident radiation. So as you decrease the solar incident radiation, the curve actually decreases, the curve falls. So you see the red curve above is at 1000 watt per meter squared, and the orange curve is at 400 watt per meter squared. So you see the decrease, and you'll find later that this decrease is actually almost proportional. Now, the next is the variation with temperature. Now, the variation with temperature is actually a little counterintuitive. For example, at low temperature is this last gray curve, right? And as the temperature increases, the curve moves inwards. So you see the orange curve here is at 65 degrees Celsius. And the reason is because the lower the temperature of the cell, the more efficient the cell is. And the reason for that is when you look at the temperature characteristics. When you look at the temperature characteristics, there are three characteristics. One is the variation of the maximum power with per degree Celsius rise in temperature, which is negative, right? So as you increase the temperature, the output of the cell decreases. Then the next is the output open circuit voltage. And if you see, the open circuit voltage decreases with increase in temperature. It's negative. So, and that's what you see here. As you increase the temperature, the curve moves inwards. So therefore, the open circuit voltage is actually decreasing. On the other hand, the current actually increases with increase in temperature. So that's what you see here. This gray curve is all the way at the bottom. As you increase the temperature, the current actually increases. Okay, so now that we've talked about the characteristics, let's talk about what it actually means from a circuit perspective. Now on the left hand side, I have a solar panel, which is right now open circuit, but need not be, it can be connected to a load. Now, what these characteristics mean, that let us consider that the solar incident radiation G is constant at some value. The temperature of the cell is also constant at some value. And in that case, what you get is a solar panel characteristic such as this. This is a panel characteristic. Now, what does that actually mean for a solar panel? What this means is that for a solar panel, for a particular solar incident radiation and a certain cell temperature, the operating point will always remain on this curve. So, unlike a battery where you just have a voltage source and you connect a resistance and the current is only determined by almost by the external resistance as long as the battery has charge, a solar panel is totally different. In a solar panel, the voltage of the panel is a function of the current, and the current of the panel is a function of the voltage. Of course, these functions are different, but that is one of the factors. What that means is if I connect a resistance to this solar panel, then technically, let's say we start from open circuit. So if we start at open circuit, we are starting at this point. So talk about open circuit and short circuit. We will talk about it soon. We start from point A at open circuit, and as the current increases, we move along this characteristic. Finally, this point will stop somewhere. Could be anywhere on this characteristic, but it has to be on the characteristic such that Ohm's law is satisfied. That is, VPV is equal to IPV into R, the resistance. Now, that's one aspect. The second aspect is, unlike most other sources, you can actually short a solar panel. So you can actually connect a short between these two and you won't damage the panel. You don't want to do that to a battery. You short circuit a battery, either you will damage it or you may even cause a fire and an explosion. So you do not want to do that. But with the solar panel, you can actually short circuit. And when you short circuit it, the voltage of the panel is 0, but the current is equal to the short circuit current. So there will be a finite current flowing through. And similarly, when you open circuit the panel, there will be no current flowing through the panel because there is no load, but the voltage will be equal to the open circuit voltage. So these are the two extreme points. And the total characteristic can be divided into 3 zones marked with these 3 circles. So in the first zone marked here, it is characterized by a high voltage and a reasonably low current. Of course, here the current is still fairly high. Then the next extreme zone is this circle here. This is characterized by high current but very rapidly decreasing voltage. As you can see, this has a very high slope. Here the slope is very high with the current. So the voltage is high, but the current is rapidly changing. And it is this zone here which is of importance. Here the slope is what you could say nominal. But most importantly, this is where you get the maximum power from the solar panel, particularly this point C. This is your maximum power point. It almost seems like the knee point of even like a BH curve for transformer. This is the maximum power point. And when I show you the simulations, you'll see exactly that's what happens. The power goes somehow this way. And that maximum power point occurs here. And the objective of controlling the solar panel is to make sure that the operating point is here. That is, we apply a voltage or we draw a current such that we are always at this operating point. So if we set the voltage of the panel, we automatically set the current of the panel. So if the voltage of the panel is corresponding to this point, we have automatically set the current, and this becomes a maximum operating point, and vice versa. If we somehow manage to set the panel current IPV equal to the value at this point, we will end up setting the voltage of the panel. So setting one variable sets the other, and that is how we achieve maximum power point tracking, which of course will be another tutorial. But here we just talk about the characteristics of the solar panel. So now that we talked about the characteristics of the solar panel, let's talk about the actual equivalent circuit we're going to use to get these characteristics. So you will find this in many papers, and it's pretty simple. First and foremost, you have a current source. This current source is of course the most important part of this entire equivalent circuit. This is what is actually generated. It is called the iridescent current or the photocurrent. And this is dependent on the incident solar radiation, the temperature, and a few other factors. We'll look into it later. Then next, there is a diode. And this diode is the most complicated and tricky part of this entire model. The last two are the resistances. These are actually just to model the losses in the solar panel, because a solar panel is not absolutely 100% efficient. It will have some loss. So to model these losses, we include two resistances. And at the end, what we get at the output is the panel voltage and the panel current, IPV and BPV. So let's start by describing how we get these. So first, the equations to describe this. Now, before that, I'll just say that what we're going to simulate is a Canadian solar panel that is called by this name CS6K275M. What that means is it's a Canadian solar panel. It is 60 cells and it is 275 watts of maximum power at STC. So I'll just list out the parameters that are most important. There are lots of parameters. You can go and look at the website, and that's also, for that matter, the screenshot which I showed before. So the open circuit voltage at STC, short circuit current at STC, the maximum power point voltage at STC, maximum power point current at STC. Most important are the first two, and I'll tell you why. Then the next is the temperature coefficient for the short circuit current. We call this alpha T. And as you can see, it is a percentage. It is not an absolute value. It's a percentage with respect to temperature. Then the temperature coefficient for open circuit voltage, we call this beta T. And again, this is also a percentage with respect to temperature, but this is negative. And last, it is a number of cells. This is a manufacturer specifications. There is nothing else to know about. It's 60 cells in the module. That's it. So now let's start with the equations. The first equation is that of the photocurrent or the iridescent current. So that's given by this equation. Here, IIRref, that is the iridescent current at STC. STC, as you know, standard test conditions, where G is equal to Gref, 1000 watts per meter squared, and temperature of the cell is equal to Tref, which is 25 degrees Celsius. So you can see it is proportional. So it is proportional to the ratio of incident solar radiation, G, and that at STC, Gref. So this is why you can see the curve actually drops as incident solar radiation falls. But anyway, more on that later. And then of course there is a factor relating to temperature. So since alpha T is positive, as temperature increases, this iridescent current will actually increase. Then the next part is the diode. Now this diode is simply solid state physics. If you want to know, just go and look up how a diode works. I won't go into that much detail here, but simply a few basics is I naught is the constant, which I'll talk about later. Q is the charge of an electron. That's just a constant. K is the Boltzmann's constant. That's also another constant known as that. T cell is the temperature of the cell. N cells is the number of cells, which is 60 in this case. The last factor which needs to be known is this small n. And this N is the ideality factor of the diode. Now this is very specific to solid state physics. I won't go into that much detail, but at a later stage I'll tell you how we can use this as a simple approximation to find out what we need to know. Now eventually what this means is VPV plus IPV-RS, if you look at this, is nothing but the voltage across the diode, because this is the panel voltage, this is the panel current. Panel voltage plus the drop across this resistance will be the voltage across the diode. So all this means is this diode current can be expressed as the voltage across the drop plus these factors, which is an exponent of these, and multiplied by this constant. Now the problem here is we don't know either of these, that is IIRF and I naught are not known. The others are constants or are measured values, but these two are not known. We need to calculate that, and we also don't know N. More on this later. So now we said we don't know what IO is, but I naught, which is in the diode current, can actually be expressed in this manner. Now again, a very non-linear equation, another exponent, which is also another exponent before, so not very easy to continue. So first is I naught ref is this diode current at STC, which means G is equal to 1000 watt per meter squared, T ref is equal to 25 degrees Celsius. So it is a function of cubic function of the cell temperature with respect to STC temperature, and an exponent of this ratio with respect to the ratio of the actual, with respect to STC with respect to the actual ratio of the cell temperature. What are these? Q and K I've already talked about. Q is the charge of electron, K is the Boltzmann's constant. EG is called the bandgap energy. Again, a very solid state device characteristic. This is the actual band gap in the diode due to that dispersion factor, or rather the barrier junction. So here we call EG in this particular is by this equation, and as you can see, it's another nonlinear equation which is related to the square of the temperature of the cell. And then to calculate the cell of the temperature of the cell, we have this equation. This equation is nothing but the ambient temperature plus the nominal operating cell temperature. It could also be NMOT. Like I said, these two are interchangeable. So NOCT can be NMOT, and G is the actual solar incident radiation. So as you can now, simply speaking, if you look at it, it's a very, very nonlinear set of equations. And if we calculate all this, we can actually calculate the current of the solar panel. That is basically the difference between the iridescent current, the diode current, and the drop across the parallel resistance. So the problem is here. We need to calculate IIRR, which is again not very easy because we don't know the constants. I diode, as I've shown before, is a very highly nonlinear current, a highly nonlinear equation. So we need to calculate that. Now, the way to do this is usually we need to calculate these factors. Okay, diode ideality factor, iridescent current at STC not provided by the manufacturer. Diode current at STC also not provided by the manufacturer. Parallel resistance component loss also not provided, and RS, these are not provided. All the manufacturer tells you is what is the power at maximum power point at STC and nominal operating module temperature. It does not tell you other things. What we would normally do is we would take all these equations that we've actually derived before and solve them. Now, these are non-linear equations. If they were linear equations, you could just solve them simultaneously. But with a non-linear set of equations, we have to solve them by some technique like Newton-Raphson method. Now, if you look at a paper on solid-state device physics, they will actually do so. That is, they will actually solve this entire set of equations with Newton-Raphson method and obtain all these constants. If you want, you could check out those papers and you could try it out, but I'll tell you an easy way to do it. To begin with, we're going to make a number of approximations. So the first approximation is this diode ideality factor. Now, diode ideality factor, from what I've read, varies between 1.2 and 2, and it depends on the doping factor of the solar panel. You could use several values, but most often people use this value of 1.3. Of course, you could change this and check it out, not a problem. but I'm going to start with this. I'm going to assume the diode ideality factor to be 1.3. Okay, so now the next step is to determine the loss components, that is the resistive loss Rs and the parallel resistance Rb. Now, as before, the way to do this is by solving nonlinear equations, but a simpler way to do this and reasonably efficient is, let us consider the datasheet values, that is the maximum power of the solar panel at STC, which is 275 watts, the panel current at the maximum point at STC, which is 8.80 amperes, and the maximum power point voltage, which is 31.3 volts. These are datasheet parameters given to you by the manufacturer, so you could kind of use them. At this, let us assume that the solar panel has 97% efficiency, which means it has a 3% loss. And also, let us make this assumption that the loss is distributed equally between the series resistance and the parallel resistance. May not be so, but I would say it's a reasonable assumption. If that is the case, all we need to do is take 1.5% of the loss for each resistance and calculate their values. And these are the resultant values. So as you can see, these values are reasonably approximate. For example, one is 53 milliohms and the other is 245 ohms. Those seem reasonable values. So therefore, we will use these in our calculations. Now, to calculate this iridescent current at short circuit at STC, that is IRR ref. Now, this is not provided by the manufacturer, but we can use a condition to assume this. Let's say, for example, let's say we short the solar panel, which, as I said, is perfectly possible. You can short circuit a solar panel. You can't short circuit a battery or any other source, but a solar panel, yes, you can. So when you short circuit a solar panel at STC, let's say supposing we are at STC, what that means is the panel voltage is 0 and the panel current is ISC corresponding to the STC value. This is provided by the manufacturer. We can just pick it off the datasheet. Now, let's say we have this condition. What does that actually mean for the circuit? When you short circuit the panel, this diode is almost short circuit. Of course, it will have a small voltage because there is a short circuit current flowing across RSC. So even though voltage of the panel is 0, there will be a small drop, which means there will be a small voltage. But this, as we said, RS is 50 milliohms. So even if we have a 10 ampere current, we are looking at a 0.5 volt of voltage across the diode, which can be neglected. So we can say that this diode is short circuited. What that means is the entire iridescent current which is generated, and iridescent current is always generated as long as there is solar incident radiation and there is a temperature which is above 0. This current has to flow somewhere, and where it flows through the short circuit, because the diode has 0 voltage, it does not conduct, and all the current flows through this. Really speaking, it doesn't happen. Some current will flow through the diode, but if we neglect this, all the current of the iridescent that is generated flows through the short circuit. What that means is at STC, your iridescent current IIRF is equal to the short circuit current at STC, because the whole thing flows through the short circuit. And that's what we do. We use this relation. What that means is IRRF is equal to ISC at short circuit at STC. And what that means is we are now able to pick this value off the data sheet and assign it to this constant. So that's one constant out of the way. So now let's move on. Now we need to find out I naught ref. For this, we take the opposite condition. That is, what happens at open circuit? At open circuit, your current is 0. I haven't specified, but IPV is 0 because there's nothing here. Voltage is equal to the open circuit voltage. Now let's say we take this at STC, because after all we are interested in the STC. That's what this constant is at. So at STC, this is open circuit voltage provided by the datasheet, provided by the manufacturer in the datasheet. What happens to this? All the current which is generated by the iridescent current which is generated by the PV panel has to go somewhere. It cannot go out of the terminal because it's open circuit. This resistance RP is very large. the way to go, the path of least resistance, and that path of least resistance is this diode. That means a small amount of it will go into the parallel resistance, but if we neglect this resistance, almost the entire amount can be assumed to flow through the diode, and that's what this is. The diode current is equal to this value, I naught into, as I said before, solid state physics equation. At STC, what we are going to say is that this IIRRF, to be precise, we can even take this RP into account, and we say that this equation is basically I naught ref. Okay, we are replacing I naught here by I naught ref, and we are saying half of it apart, not half of it, I'm not saying, sorry, that's totally wrong. A large part of it flows through the diode, a small part of it flows through the parallel resistance. This is the part flowing through the diode, this is the part of it flowing through the diode, through the parallel resistance. I naught replaced by I naught ref for STC, VOC, because there is no current, IPV is 0, and since it is STC, VPV is equal to VOC. This means we have all the parameters here, and we've already assumed n. That means using this, we know this value because we've already calculated before. This value is equal to the short circuit current at STC. We know all the values except for I naught ref, which means we can calculate I naught ref, and that's the equation. All we have to do is rearrange this equation. So with this, it can be calculated. Of course, we need to calculate it. It's not straight away picked out from the data sheet, but it's not a very difficult calculation. It's a one-time calculation. We don't have to repeat it all the time. This is just from the data sheet. So with this done, we now have all the values we need. We have the diode ideality factor, we have the iridescent current at STC, diode current at STC, everything. So let's get started. First part, temperature of the cell. We have the ambient temperature, which is, let's say, atmospheric temperature, which can be measured, calculated by these values. NOCT is a datasheet value, G is measured because it's the solar incident radiation. There are meters which measure this. We can, after calculating this, we can then put it into this value. That is, we have already assumed this, or rather calculated. This is equal to the short circuit at STC. G is measured. T cell has been calculated here. We have all the values we need to calculate the iridescent current. That's wonderful. The next step, we'd use the same value of T cell into this equation for bandgap energy. Since that's the only variable involved here, we can calculate the bandgap energy. These equations, if you want to know the details, go and read any book on solid state physics. I can't talk about it here because eventually what we need to know is how do we design a solar panel. Now, the next step, we know EG, we know T cell. We can now calculate the diode current because, as I said, we've already calculated I naught ref. I naught ref has been calculated from the previous equation. So we know we know all the values here. We can calculate this value. What that means is we now can calculate the diode current and we calculate the iridescent current using these values. And that means we have IPV to be calculated. It's the difference between iridescent current, diode current, and the current through the parallel resistance. Now, here you might be a little surprised because IPV exists in both these. Alright? What that only means is it's an iterative method. This IPV is the current value as a current value of the current iteration, whereas this is the value of the previous iteration. So we are always doing n plus 1 with respect to the value at n. So eventually what we get is this is the equivalent circuit of the PV panel. The entire thing on the left hand side, the diode, all that, we don't model it. What we model is this. There is a controllable voltage, alright. There is a resistance here, which is a nominal resistance, and the panel current. What we have is this panel current. So eventually the entire PV panel is modeled as a controllable current source. This controllable current source will take into account the measured value of the PV voltage. Alright, we do not generate the PV voltage by any equation, we measure it. It is measured and put into this equation, and the previous value of the PV current is taken to calculate the present value of the PV current. Now you might ask, why this capacitor? The reason is we are measuring the voltage across the PV panel. Measuring the voltage across a PV panel just if there is a resistance in another part of the circuit may result in an unstable value. The best way to get the stable value for this is place a small capacitor, as this capacitor will stabilize the voltage and give you a stable value always. You might otherwise, without the capacitor, end up with some amount of jitter. Try it out and check it out for yourself. So this is the value of the generated voltage that we need once we calculate at IPV. This is how we model the solar panel. So to simulate this, all I do is I start with a short circuit. Well, I can't really short circuit the panel, but I can actually connect like a negligible resistance like 1 milliohm or 10 milliohm. I gradually increase the resistance until it becomes several hundred ohms, in which case the solar panel almost goes into open circuit voltage. So you see, this is short circuit, voltage is almost zero, current is near the short circuit value, and this is very important. You see, the current is at the short circuit value, it's not dangerously high. In a battery, this would be dangerously high, which means it could damage the battery. Short circuit, but with a PV panel, not so. As we increase the resistance, the current decreases, voltage increases, and finally this is, and I would say somewhere here would be a maximum power point, right? And if instead of mapping it with time, we map these two variables with respect to each other, that is, we take the PV voltage on the x-axis, we take the PV current on the y-axis, we'll get this characteristic. Now you might ask, what is this jitter? And even I did. The reason, there's two. One, the value of resistance. It's how we change it. I'm changing this value of resistance almost gradually. I have a code with a variable value of resistance which is changing this value gradually, but really speaking, at this point you need a very fine control of the resistance, and if you don't, we have some amount of jitter. The second reason for the jitter is of course the model. Our model is an approximate model and not a perfect model, and also two, it depends on how often you run this model. In the simulation, if you download the simulation files, or if you purchase them rather, you will find that I have calculated this PV panel at a 1 microsecond time step. You can change this and check it out. Again, these are different things you can try out. So to check out if we can actually mimic the PV panel characteristics that the manufacturers provide, have a look at this. This is when I decrease the solar incidence. This is at standard test condition, that is the last highest one. This is at 1000 watt per meter squared. As I decrease it, you'll see the curve drops, and it's almost proportional. It's almost exactly the way the manufacturer supplies it. And if you look at this, this is the maximum power point. You see, the maximum power point remains at almost the same open circuit voltage. It is almost dropping proportionally. Alright. And with this, I end my presentation. Thank you so much for listening. And if you would like additional information, check out these three links. One is the homepage of the project, which is pythonpowerelectronics.com, or you could check out the Facebook page, which is basically on Facebook, Python Power Electronics related to Facebook. And the third link is my Gumroad account, that is gumroad.com/shiftKIR. This is where I have listed the simulation files with this tutorial, and also there are several other simulation files if you would like to check it out. And that's all from me. Thank you so much for viewing.